All right, what we're going to start on now is applying what we've learned and actually making some use of it. And we get to start playing with some electronics and seeing how these things work in real life. So I'm going to start with the object I've drawn on the top. This little guy here. Why is that a square? That should not be there. This little guy here. There we go. Okay. We've lost all control. Let's try this again. This guy here. There we are. Okay, this is the parallel plates just like we've done before. And in the parallel plates I talked about in the last few videos, the electric fields are constant between. And the way to think about that is that I'm going to have equal and opposite charges on both sides of the plates, even distribution. So my field lines are going to go from one right into another, and I end up with these field lines that go kind of like this. Right? What I placed in there, that little circle, we're going to call a perfect conductor. A perfect conductor, remember, allows the flow of electrons to move freely about the building, and that means that I can have a shift happening with my charge. The way we like to describe that is that the charges accumulate on the surface if there is charge in a conductor. This one is just going to start off neutral. And so what do I have? I've placed this thing inside of these parallel plates. I'm going to have E fields, so electric fields coming out of the positive and heading towards the conductor. So what's going to happen to the conductor itself? Well, how do electric field lines go? They go from a positive into a negative. So I'd end up like with negative charges kind of building up over on that side. Remember the polarization, that whole part of the thing we were talking about on exam 1 and some of the subsequent quizzes we've done. If this thing is neutral and nothing is touching it to transfer charge, the electric field won't transfer charge, but it will polarize it. So if I move, say, 3 electrons to that side of the sphere, I'm going to end up with this positive charged other side of the sphere. So what happens with that shift? What's happening with the electric field inside of that sphere? Well, let's see, they go from positive into negative. From positive into negative. Oh dear. So what happens on this side then is now my electric field kind of continues on. And if I take a voltmeter and I touch the inside of that, and the way we do that is like a graphite pencil, or special conductor pencils that we can get, and we draw a circle on the graphite paper that conducts. And if you can take your voltmeter and place it inside that circle and measure the potential difference, what you'll see is the potential difference is 0. And if it's 0, then that means the electric field is 0. Oh, so how is that happening? Well, because if I think of this in terms of the vectors that I have going on here, what happens inside the conductor is precisely canceling out what's happening on the outside of the conductor. So I have no electric fields inside of the conductor. It's the way to say that, or the other way to look at it is those vector quantities cancel, and I'm therefore measuring 0. One of the better ways I've heard it explained is that if I place a conductor inside of an electric field, no matter how odd shaped that conductor is, I'm going to have points all around it that are going to balance out with positives and negatives. So if I have a field on this side, it's going to have the opposite thing happening on the opposite side, and anything that can be there by symmetry is going to cancel out. No matter how odd the shape is that you make, if you put a conductor in the field, that's what happens, and it's pretty cool. So we get all that going. Fun. So let's remind ourselves. We talk about current going from a high potential to a low potential. And I've hinted at this thing, minus the little sphere in the middle, because why would we do that, that we call this thing a parallel plate capacitor. I temporarily could not spell capacitor. I think that's right. And another way to think about that is if you see our plus and our minus signs, is that I have encouraged the fleeing of electrons from this side, and I'm going to have electrons gathering on this side. To me, it's easier to think about in terms of this thing that we call current, the flow of charge. I'm going to talk about it in terms of positive charges simply to keep everything consistent, but I do want to remind that it's electrons that are actually moving, or how we define electrons. And now I totally don't know why I wanted to draw that. Let's come back here because this is more exciting. So this is just a battery. And we refer to the positive terminal as being the high potential, and the negative terminal as being the low potential. So if I connect two wires to both of those terminals, I can get current to flow. So let's just, it makes me ill, but we're going to have little positive charges coming out here. And then they're going to kind of gather here as much as they can, because we still have forces going on. And so remember that I can't, okay, two magnets. If I take two magnets and they're the same charge, same polarity, and I push them together, you can feel that little pocket of resistance happening in between them. Well, there's like this maximum amount that you can push them, but before you actually crush the magnets themselves. In electrostatics, the same thing happens. I can't force more charge to gather on a plate or in an area than that charge has an ability to separate itself out and minimize that repulsion. So for this, I'm going to have like this maximum amount of positive charge I can get on the one plate. And what's going to happen on the other? Well, polarization. Remember, we're still saying that positive charges are moving. Ugh. So the positive charges are moving, and I'm leaving electrons behind. Okay, so now I have this attraction. So I have not just positive charges. I can get a little bit more positive on there because there's also attraction. Still a limit, but I can get a little bit more there. What is really cool is that the maximum amount I can put on these plates, once the thing is what we call completely charged, this potential difference is going to be exactly the same as this potential difference. Let's think about why that is. So I have a high and a low potential. So I have as much movement as I can generate from that potential, as high as that cliff can get. And I'm going to let the water go into a pool below. Well, I can only get as much potential here as I had from here. And in terms of electrostatics, that's where the whole water thing kind of falls apart, is that I have a certain amount of difference that I can work with, a certain amount of difference that can work with a charge Q. And this plate then will collect that difference. What happens then when this thing equals this thing? Everything stops. Nothing flows anymore. That's one of those that I like to think in terms of where the water comparison comes into handy, is if you think of a waterfall close to a lake, right? So I can get a considerable amount of water going into the lake, and then I'll have flow at the bottom. But if suddenly my lake becomes even with my water, I no longer have any flow. There's no difference in height there to allow for that flow to happen. And the same thing is what would be happening here with our capacitor plate. We are going to define these capacitor plates with this letter C, which is not helpful. I realize this because charges in terms of coulombs. So I apologize in advance. Sorry about that. Give me a second. So we have the capacitor plate, and let's think of how we can physically define this. Well, if I have a constant electric field, and that is from the positive into the negative, so the same thing that is happening here on a much smaller scale that is happening here minus the little sphere. So what do I have? I have like this epsilon naught times the area of the plates divided by the distance of separation. And this should look familiar because we came up with something similar with that, with just a single plate or parallel plates 2 chapters ago for the electric fields. So a capacitor then is defined by the shape of the capacitor, which we always use these plates, and the distance between the 2 plates. Now what we actually do is not just have air in between there, we put something else called the dielectric, and we'll go into more detail on that Wednesday. And so with the dielectric, actually I'll go ahead and talk just conceptually about it now, and we'll end here. With the dielectric, I can put something in there that say as like water. Water is polar, right? So we've talked about that before, where I have my electrons like this, and then my 2 hydrogens. So if I put something like this, water, into my plates, which you wouldn't, electronics don't want to do it, what's going to happen? Well, these negative electrons would align themselves with these positive charges. And the hydrogens, these positive charges from the hydrogens, would align themselves with those negative charges. What that does is help increase attraction, which allows us to get more charge onto those plates. The separation distance, we try to keep that teeny, teeny, tiny small. It's on the bottom, so the way to think about that is the smaller it is, the larger the number is going to be for my capacitance, for my capacitor, my parallel plates. The other way to think about that is that the closer that distance is, the more influence I have to optimize my attraction between my positive and my negative charges. What's important to remember, though, is that the distance helps with the capacitance, but the electric field still stays constant between the plates no matter how far apart they get. So I can decrease capacitance, but the electric field will stay the same, minus the little fringy stuff that happens on the sides. So what we're going to do on Wednesday is we are going to take this concept of capacitance, and I'm going to introduce this thing called Kirkhoff's rules. Oh my goodness, why did I just write this down? I don't even know if I'm spelling his name correct. Hopefully that is. And what Kirkhoff's rules, to start off with, is just going to tell us is that once I go around a loop, so like this little thing that I've created here, that from beginning to end, whatever I start with, I'm ending up with 0. And that is going to be a very powerful tool. In a way, I just described that with my delta V's, right? I said, so when this delta V equals this delta V, my water has come up equal with the waterfall, I have no flow. So once I've used up all that potential, I'm like raising the layer of the link, everything goes away. And all that comes down to conservation of charge and energy, which is very fun. And so that's what we're going to do on Wednesday. We'll do math with that. This is just your introduction to get excited about it.